This is required practical 9. Investigate what happens when aqueous solutions are electrolyzed using inert electrodes. So this comes up in several specifications, including the AQA Trilogy and AQA Chemistry awards. And what we're going to have here are 3 different examples of electrolysis where students are needed to predict what the products are each electrode with an explanation. So in the first case, we've got the most simple one here. This is copper chloride. And just to take us through the basic circuit, there are different ways to do this, but we've got a power pack on 6 volts. You can use batteries, but I think power packs are much easier. We've got an electrolysis cell. This is a particularly good one, but you can just use beakers with a piece of cardboard to hold the electrodes. Upside down test tubes are fine. And we've got our 2 graphite electrodes, which are the inert electrodes because they're not going to react with the solutions. And we can start just simply by tracing through to say which one is the anode and cathode. So we've got our acronym PANIC, positive anode, so red is positive. So this one's going to be the anode, and the PA is positive anode, and then negative cathode from PANIC. Okay, the black wire is the negative, so this is the cathode. So the first thing to talk about is, of course, what do you get when copper chloride is dissolved in an aqueous solution? And the formula for copper chloride is CuCl2. So you get 2 Cl minus ions. It's minus because it's group 7. Group 7 all form -1 ions because they're non-metals and are in group 7. And copper, well, copper's a transition metal, so you're not required to remember what sort of ions it produces, but you can tell it's +2, because chlorine is minus and there are 2 chlorines. So if there are 2 chlorines which are both minus, that's -2, and that means the copper must be +2 to balance it out to make an ionic compound. So that's the ions. So we've got copper Cu2+ and Cl- going on in there. And so if we switch on our power pack, as a warning for this practical, that we have the first product which is going to be produced at the anode is going to be chlorine gas. Now, collecting the chlorine gas in an upside down tube does make it a little bit safer, but it does mean that so it's going to be safer, and if you don't collect it in an upside down tube, it is safe in a lab. You don't have to do it in a fume cupboard. That's absolutely fine. So you should be able to see that there are bubbles being produced there. It's not going too fast at the moment, and I think the reason really it's not going as fast as it should be is because we've got the bulb taking a little bit of the voltage here, because the voltage is being divided. So I'm going to turn that up a bit, okay, to about 10. Normally I'd run this on 6 without the bulb, but the bulb's quite good because it tells you that there's an electrical current flowing. So obviously we can see there are bubbles of gas, nice streaming bubbles of gas being produced there, and we're getting chlorine gas produced here. And then on the cathode, we should, over time, and it takes a little bit of time for this, but over time we should get a slightly red tinge to the graphite electrode, which will be the copper plating directly on here. So why are we getting chlorine and why are we getting copper? Well, copper is less reactive than hydrogen on our reactivity series. Here's our reactivity series. Copper is below hydrogen, along with silver, gold and platinum, and that means you get the metal produced at the cathode. At the anode, if there is a halogen ion, so chlorine, fluorine, bromine or iodine, then you're going to get that produced. Obviously chlorine is going to be a gas. Iodine and bromine will both form aqueous solutions but will discolour the water. You wouldn't want to make fluorine, it's very dangerous. So after a while of running this, we can get enough to test with a gas test. So we go to the second example, which is a bit more complicated. Over here we have potassium bromide. Now this time potassium is more reactive than hydrogen. Now because it's more reactive than hydrogen, when we switch on the apparatus now, we're going to find here at the cathode you're getting a streaming bubble of gas. You're not getting a metal plated on here because potassium is more reactive than hydrogen, so the hydrogen gets produced instead. The hydrogen can be tested using a lighted splint for the squeaky pop test. Key things there for the exam question: you have to say lighted splint, you can't say lighted match, and you have to say ignite with a squeaky pop, and it has to be squeaky pop. Keywords. Now you can notice on the anode, the positive electrode here, that we're getting this brownish tinge from the bromine, which is forming and then dissolving into the water to form this brownish colour. We're getting bromine because bromine is a halogen, and if you have halogens in the halogen ions in solution, the halogen will always be produced. But we're not getting potassium because potassium is more reactive than hydrogen. So that's that one. And again, we've got the light just to show it working. And our final one, the most complex one, sodium sulfate. So sodium is more reactive than hydrogen, and sulfate is not a halogen. So what do we get in the case of this one? So first of all, at the positive electrode, okay, so at the positive electrode here, the anode, we're getting a gas produced. And that gas that's being produced there is going to be oxygen. Why? Well, if it's not a halogen in solution, so if it's not chlorine, fluorine, bromine or iodine, then you always get oxygen. So if you're doing electrolysis of anything like sodium sulfate, or you're doing potassium nitrate, or anything that has not got halogens, then you'll always get oxygen at the anode. Now the gas again is collecting on the surface, in the tube, and we can test for oxygen by taking a splint, blowing it out so it's glowing, putting it into the tube, and it will reignite. And again, for the exam marks, you need to be clear on all of those things. So glowing splint placed in the tube, and it will reignite. We're also getting a gas produced at the cathode, and the cathode is going to again be hydrogen gas because sodium is more reactive than hydrogen, so the hydrogen gets produced instead. So the other question to ask is actually what's going on at each electrode. So we've got this process called discharging. So in this case of the copper chloride, the chloride ions are Cl-. So the Cl- go to the anode and they give away one of their electrons. So Cl- becomes Cl and forms with another chloride atom to become Cl2. So we can write a half equation for that, and the half equation would be 2Cl- plus, minus 2 electrons, minus 2E- goes to Cl2 gas. Then at the anode, and at the cathode, we've got the copper, and the copper is Cu2+, so it wants to have electrons, so Cu2+ plus 2 electrons goes to Cu as a solid, and then we'll plate the electrons and become a non-charged atom. So going back to the copper one, you can actually now see where we're getting a bit of a brown tinge to the electrode. And that will take some time to do that. And over time, the whole electrode will become brown. Okay, so safety advice for the practical, which is important for everybody, is that we've got two real main safety issues. One is, of course, the danger of the chemicals, which are harmful. So we should be wearing goggles, safety spectacles at all times. We're also dealing with electrical current, so at no time while the apparatus is turned on should you touch the electrolyte solution, because that could issue you with a shock, nor should you operate the controls on the power pack with wet fingers, because then that could give you a shock as well. The only other safety advice that you could say about this, of course, is the general not eating or drinking in the lab. But really the best two to put down on an exam question that came up would be wear goggles because they're harmful, and to not touch the electrolyte solution during the operation because it will provide an electric shock. Okay, so we're just going to do the gas test here. We've got some blue litmus paper here, and we're just going to turn off our power pack. And then we're going to take our chlorine. Chlorine's heavier than air, so when you take it out, you should make sure you put your finger over the top as quickly as possible to make sure the gas doesn't escape. And then we'll basically just pour the gas out. The gas will basically diffuse out, and it will turn the paper red as the chlorine reacts with the water to form hydrochloric acid, but then it eventually will bleach the colour from the paper completely. So here we go. Going to leave that on there. It's very pungent. Remember, one of the safety advice here is you should not inhale directly, just waft the gas. And I can see that I've got a red patch there forming on my paper, and eventually that red patch will just go pale as it's bleached. So that's our test for chlorine. And that was only produced after about 5 minutes. Didn't take long to produce the chlorine. So now we're going to do the other tests. So for the first test, we're going to light a splint, and we're going to take the hydrogen. Now hydrogen is less dense than air, so we can, when we take the tube out, we can just keep the tube upside down. We use a lighted splint, and we have to say lighted splint. Candidates won't get a mark for saying use a match. Okay, and here's the hydrogen. It's upside down because it's light right now. All I have to do is turn it right way up and put the splint at the surface, and we get the squeaky pop. And I have to say squeaky pop. Our last test is going to be for the oxygen, and I don't think I've collected enough oxygen gas to do the test, but the oxygen one would be to take a splint that's glowing. Again, just lighting a splint here. And then you want to blow it up, but have it glowing like this. And then when you put that into the oxygen, which we should have had formed here, okay, then that will reignite, but I don't think we've got enough. Oh, it is glowing slightly. It glowed slightly, but it will reignite if there was enough oxygen present. So that's required practical 9. And just to remember, students need to be able to draw a circuit diagram of this apparatus. They need to be able to say what ions are formed when an ionic compound is dissolved to form an aqueous solution. And then they need to predict what products are going to be produced at the anode and cathode, using those simple rules that if it's a halogen, then halogen's produced. If it's not a halogen, then it's oxygen produced, that's at the anode. And then at the cathode, if it's less reactive than hydrogen, then that metal is produced, which is only going to be copper, silver, gold, and platinum. And then if it's more reactive than hydrogen, then hydrogen gas will be produced.